Okay, I think we'll get started. So today we're going to talk about Le Chatelier's principle from a quantitative point of view. So we learned about it a couple of lectures ago, and as you're developing your chemical intuition, Le Chatelier's principle is very important in all sorts of settings. And there we had a qualitative picture. Say, okay, we make a disturbance, the reaction will shift to minimize that disturbance, come back to equilibrium. So if we were to, say, add reactants, then our reaction would shift to push the reaction forward to reduce that disturbance and reestablish an equilibrium. That's all a qualitative picture, and that's what our book, whatever book you have, will be talking about. But I want to talk about here a quantitative way to do this. And this is not going to be in your general chemistry book. I have a bunch of extra problems in the notes. So there's a homework section for this in the notes to give you some problems to work on with this. And then today here we'll go through a number of examples. All right, well, we're going to start with this version of the delta G equation. And if you remember last time, we derived this version, and I said that this is going to be important for determining Le Chatelier's principle. And it rests here on this ratio of Q over K. And notice if Q is greater than K, then this ratio is greater than 1. Log of a number greater than 1 is always positive. This is absolute temperature. This is gas constant, so that's always positive. Delta G is positive, so if Q is over K, then our reaction is going to go back towards reactants, as we know. And likewise, if Q is less than K, then this is a number less than 1. That makes the log negative, and the reaction will go forward because delta G will be negative. All right, to do this Le Chatelier's principle in a quantitative way, we've got this algorithm here. And so let's just run through the algorithm, and then it'll come into picture when we do some examples. So we identify the initial equilibrium, we introduce a disturbance, and then we determine the shift relative to that disturbance. So let's work through an example here. We've got A plus B. Here's the reaction. A plus B goes to C. We're going to double the reactant, and we'll be at 298 Kelvin. So the first step, we identify the equilibrium. A is AEQ, B is BEQ, C is CEQ. We don't know what those are, but we know those are the equilibrium concentrations because by definition we're at equilibrium here. So then our K is the products over reactants raised to their stoichiometric factors. Then we'll do the disturbance, which in this case is simply to make A go to 2 times A. And so the disturbance, we think, boom, right after the disturbance, what is Q? And that will determine our shift. So to determine our shift, we write Q. Q is the reactants, or the products over reactants. So C, EQ, that hasn't changed. BEQ hasn't changed, but we have a 2, which has got a little erased here, in the denominator here. Now, what we can notice is that aside from that 2, we have the old K. And so right after the disturbance, Q is 1/2 of K. And so then Q over K is going to be 1/2 because the K's will cancel. And then our delta G will be RT ln 1/2, which is negative. And if we plug in 298 Kelvin and the gas constant, then we get minus 1717 joules. But the big picture idea here is this is negative, right? And so we've added, we've doubled the reactant. We expect it to go forward. We got a negative delta G quantitatively, and so indeed it goes forward. Let's try another example where we dilute by a factor of 2. So we have the same reaction, we'll dilute by a factor of 2. That means we're putting pure water in. We're going to take the volume from wherever it was to twice the volume. So again, we start the equilibrium. A is AEQ, B is BEQ, C is CEQ. Now for each of these species, A, B, or C, but the disturbance is going to half the concentration. So whatever the concentration was, when we double the volume by adding pure water, we're going to get half the concentration. And so the Q, we write half of each of these. And then we can notice, we can pick out here the K 2 of the halves cancel, but we have an extra half here in the bottom, and so that's going to leave 2k. So Q over K is going to equal 2, and so we have delta G is RT ln 2, which is positive number. Happens to be 17 again, but positive. And so this says that the reaction will go backwards. And this, we can think of this based on our intuition. If we have more volume, then we're going to be able to favor the fact that this is 2 species compared to 1 species. And that is a little bit more advanced intuition about the Le Chatelier's principle. It's not one that would be as immediately obvious as this. But when we do this quantitative approach, then it comes out just automatically. All right, let's do a gas phase reaction here now, and let's compress to half the volume. And really, these are very similar types of intuition we need. We're going to half the volume, and so we start out at equilibrium. The partial pressures are the equilibrium partial pressures. The K is products over reactants again. Disturbance, we're going to cut the volume in half. That means the pressure is going to double. And again, we haven't talked about gases yet, so I'm just telling you that. Towards the end of the course here, we'll get through gases and we'll be able to calculate that. But as you might intuit, if we squeeze down the volume, the pressure is going to go up. So the new partial pressure is going to be twice the equilibrium partial pressure, so that our Q, we put in all of these, 2's will cancel, and we get 1/2 K. And again, delta G, 1/2 K. Oh, not K here, just 1/2. Because Q over K is 1/2. And so RT ln 1/2 and our minus 17.7 joules again. So this will go forward. And if we go to try to intuit this, very much, because it's like the dilution problem in reverse. A dilution is like expanding the volume. This is compressing the volume. And so we expect to favor the side that has less particles. And again, that's a higher level of sophistication in the qualitative understanding of Le Chatelier's principle, but it comes out very clearly here in the quantitative principle. So that supports the development of that intuition. All right, let's do something that would be maybe quite hard to just qualitatively determine. Let's put this reaction in a container, and then we're going to double the pressure by adding an inert gas, so adding argon or something. And the total pressure increases, but that increase in pressure is due to the partial pressure of the inert gas, which is not participating in the reaction. So the partial pressures remain the same. So Q after the disturbance is equal to K. Q over K is 1. Log of 1 is 0. And so delta G is 0. And we go neither forward nor back. We stay in equilibrium by adding that inert gas. If we don't have this, on the one hand, it's an inert gas, so it probably shouldn't affect the equilibrium, so that makes sense. But then on the other hand, we're increasing the pressure. The system should act to alleviate that by making less molecules. But this helps us determine that the inert gas won't do anything here. All right, now let's connect to exothermic and endothermic reactions. We'll do an example of this reaction. Let's say it's exothermic. This happens to be exothermic. We're going to raise the temperature. So we'll carry out our algorithm. A is AQ, B is BQ, C is CQ, K is this ratio. The disturbance is to raise the temperature. Now we have to go back to last lecture and recall that we carefully worked out that if we have an exothermic reaction and we raise the temperature, then the K is going to go down. And so this is a little bit different than what was happening over here. Our K is changing on us because we have a different temperature. but our Q is not. So the disturbance, think of Q right after the disturbance. We're going to just imagine we can snap our fingers and the temperature is higher. Q is the old K, right? Q is the old K. So if we take Q over K, we have K old. And let's just say, for the sake of example, this goes down by 10%. So it's 9/10 of the original. Then this is K old over K new, and that is going to be 9/10 of K old. And so Q over K is 10/9. And so this is positive, so this goes backwards. And if we do our intuition, we would write something like this. We put our heat on this side. We're going to add this, so that should shift the reaction backwards. And indeed, we recover that with this quantitative calculation. All right, so again, this is not something that can be found very easily. It certainly isn't in the general chemistry books. So practice this, make sure you really understand it. It really elevates your game in terms of your comprehension of Le Chatelier's principle.